Okay, welcome to lecture 8. So in the last lecture, really all the previous lectures, you became masters of everything parallel systems, parallel elements. Now we're going to talk about serial systems in this lecture, and this is where things get really exciting. Okay, so you'll recall the mathematically complete fact chart. So this was the chart I told you. This contains all freedom and constraint space types that pertain to designing parallel systems. And you know that freedom spaces contain rotations in red, screws in green, and black translation arrows. And so you see them populated with all these. But you notice up to this point, we kind of haven't shown wrenches that are orange or pure black moments. All right, we just stuck to blue constraint spaces because we use the blue things to synthesize wires, blades, and everything else you've ever seen us synthesize. So that's what's needed for parallel systems. Okay. Well, but let's take a look at one of these freedom spaces we're familiar with. Freedom constraint spaces. This constraint space is just a single blue plane. Okay, it's the constraint space of a blade, and the way we generated it from the past, you recall, we draw like lines that connected the ground to the stage, and that passed through the geometry without exiting it, and we drew all the blue lines that filled it, so it was fully filled blue. That's why it was a parallel element. And then you can linearly combine all those blue lines within there, and you'll find it will make this constraint space. Okay, so I want to teach you now a different way to kind of think about constraint spaces. Maybe you've already been thinking of them this way, but they're essentially a space that represent all the loads that the constraint is capable of resisting given its geometry. Okay, so you can think, well, could we resist this pure force along this axis? Yes, that stage could. Could it resist that force? Yes, it could. That blade flexure will cause it to resist that force. Okay, what about that force? Yes. What about this force? Yes. What if the force goes outside the geometry, though, of the blade? Can the blade only resist forces inside its geometry? Well, no, it could resist a force in this direction. If I extended this stage but kept the blade like that and grabbed it and yanked on it with a force, it could still, if these were ideal constraints, that this blade, it would still resist that force. And the reason is because it's a linear combination of all the forces from inside. They can simultaneously, you're acting on the forces inside the material linearly combined to get this force, which is exactly how you're generating the constraint space. You take all the blue lines that draw inside of it and you linearly combine them and you make an infinitely large space of all the things that it can resist. Okay, so that's an interesting thought. And then what if you pull this to infinity? Okay, what is a blue line pulled to infinity? We know if we have and first of all, can this stage resist that blue line pulled to infinity? Well, sure, it's part of the linear combination, but what does it mean, a blue line pulled to infinity? We know a red line pulled to infinity makes a red hoop that when you rotate around it, it causes a translation perpendicular to kind of the plane of the hoop. So it's really a translation, and is really a circle with an infinite radius that's infinitely far away in all directions, right? Well, a blue line can be pulled to infinity, and a blue line obviously is also a circle with an infinite radius that's at infinity in all directions. And so it can obviously mathematically done, but what does it physically mean? What is a blue line at infinity? We haven't used these as of yet, first of all, because why would you stick a wire on something that's infinitely far away? That's not even practical. You can't do that. So we haven't looked at blue hoops. But mathematically, what is a blue hoop? Okay, remember when it's red, you think of it rotating and you imagine it rotating, so you can imagine a translation. But what it now, this is a pure force. So now imagine pushing along its axis with a pure force in a circle. What you'd get is, if you're pushing in a force in all these directions, what you'd get is a moment, a pure moment. Okay? So usually you think you can only make a pure moment from 2 point forces that are equal and opposite, right? You have 2 coupled forces equal and opposite with, offset by some distance, d or something, right? Like you get the moment that d times f is what the moment is. Well, you can get a pure moment with just a single force, as long as that force is infinitely far away. The further and further you get, the more it acts like a moment. And when it is infinitely far away, it's not just a force far away that's behaving sort of like a moment. It is actually a pure moment when it is infinitely far away, and it's going to go into this like circular kind of force thing you could imagine, okay? So just like, and by the way, that's a part of the constraint space. Before we just drew the blue lines, but you can indeed, with this stage, you can, it can resist a pure moment. It can impart a pure moment to resist that. The blade does that, right? And so it's definitely part of the stage. We haven't been drawing it though, because you can't put a wire infinitely far away. But it is mathematically there, and it's a load that blade can resist. And every other force on this infinitely large plane. Okay? Okay, so let's look back at our analogs here. Remember, rotations are twists with a pitch of 0, and they're analogous with constraint lines that have a Q value of 0 that's a pure force. So even though this is an angular thing, a rotation, and this is a linear thing, they're analogous. Okay? And in like manner, when the pitch is infinite, it's a translation. Here, when the Q is infinite, it's a pure torque, or a pure moment, right? These guys are analogous, okay? Oh, I'm sorry about that S here. That S should be down there, right? Okay. Okay, and again, that's a translational thing, and this is the rotational thing. But then these are both kind of combinations of translation and rotation, and these guys are analogous. This is a twist with a non-zero, non-infinite pitch is a green screw, and a wrench with a non-zero, non-infinite Q value is an orange line, which is a wrench, coupled torque with a force along its axis, okay? Those guys are analogous, okay? And of course it makes sense if you have a red hoop and it makes a translation. It makes sense if you have a blue hoop, you have a moment, okay? Well, okay. You might also recall from past lectures that we proved that the relationship between any twist of any pitch and any wrench of any Q is P plus Q equals D tan theta. And what we did in the past was we just said, like, look, we don't care about orange and black wrenches. We just want blue wrenches, and so let's make Q 0, and we said P equals D tan theta, and we've operated from there since. But if you allow Q to be non-zero, and you take this as the grand governing equation that tells the relationship between wrenches, twists and wrenches, right? And this is like the highest, most general form of the rule of complementary patterns that tells the relationship what these things have to satisfy for any Q and any P. Then what you find is the chart fills out a little bit more. Okay, so like, first of all, you'll see, look, I added the pure force wrench thing, and you'll see nothing changed in the freedom spaces. The freedom spaces, we've always added red, green, and black in translations, screws, and rotations. But now you'll notice the constraint spaces just got a lot more complicated. They have black moments in them, they have orange stuff, orange wrenches, and they're a lot more complicated. So suddenly this chart just got a lot more crowded. But what's even more is you find if you don't make Q equal to 0 and you follow that relationship mathematically, you can actually even generate many more freedom and constraint spaces that lie outside this black pyramid, okay? And this is the complete fact chart. There's no other spaces, no other freedom and constraint spaces. They're all in there, and it turns out there are 7 columns, okay? And by the way, this little dog-eared thing is just because I couldn't fit it. In column 3, well, first of all, there's 1 in column 1. In the ZUDOF, one thing, there's 1 type. The 1DOF, there's 3 types. In the 2DOF, there's actually 10 types now. 4DOF, there's 10 types. 5DOF, there's 3 types. 6DOF, there's 1 type. In the 3DOF type, though, here's up to 10, and then it goes from 11 to 16, and then it goes from 17 to 22. So there's 22 altogether. So you stack that one on top first, then you stack the other side on top of that, and that would be correct. It's just this is much more compact to do it like that. Okay. Okay, but anyway, this is absolutely a beautiful chart if you stare at it and look at it for a while. First of all, I mean, it's neat that it is, there's the same number on each side. There's 1 here, and 3 here, and 3 here, 10 here, and 10 here, and 22 there, which makes a total of, 50. So that's cool. But it's also, it's just neat that they're all contained within 7 things. There's many cultural, religious traditions that say, 7 is usually a number that means infinite and complete. This is I could give tons of examples in religion, scripture. These kind of things in all religions seem to agree, and it's kind of cool that it's an insight that there are 6 things with a special 7th is 0. Okay, so and of course that's because bodies can have 6 degrees of freedom, or they can have no degrees of freedom, and everything in between. So everything's contained within 6 things. And the really cool thing is you start seeing that, holy cow, check out this freedom space here that's empty, 0 degrees of freedom, is obviously the same as the constraint space over here that's empty. If you have 6 degrees of freedom, you have no constraints. And therefore its freedom space is the same as its constraint space. Then you look here and you say, my goodness, look at this translation, which from that previous slide, translations are analogous to pure moments, and blue lines are analogous to red lines, and green lines are analogous to orange lines. My goodness, check it out. The freedom space is the same as the constraint space over here. And the freedom space here is the same as the constraint space here. And it goes all the way down. Every single one of these, look, green to orange, blue to red, and they're all symmetric about the 3rd case. You can see here, look at this one and this one look the same, and that one look the same. This and this will look the same, that one look the same. This one look the same, that one look the same, and they're just different complementary colors. This symmetry is so strong, in fact, that it explains why the 3rd column, everything looks the same. Have you ever wondered, like, my goodness, the freedom and constraint space of these in these columns and these columns and these columns look completely different, but look at this. Sphere, sphere, box, box, plane, plane. Everything, even those interconnected disks, they look the same. And the reason is because everything is symmetric even about the 3rd case. This is symmetric to that, this is symmetric to that, this is symmetric to that. And the rings do some tricky, fancy things to get them to be symmetric, but all of the constraint and freedom spaces kind of look the same in the 3rd column because they're symmetric about themselves. And then everything else is kind of symmetric about this. The freedom constraint spaces are symmetric about the center. So it's a really beautifully organized chart, and it kind of tells itself that it's complete in many ways. And you'll find that the chart is even more beautiful. But this is the mathematically complete chart of freedom constraint spaces when you consider all kinds of wrenches and all kinds of twists. Okay, so let's see if I want to say anything more about this chart at this point. Yeah, I'll be talking a lot more about this in episode 11. Really cool things to notice in this chart beyond what I've already told you. Anyway, so this is the whole mathematically complete story. But again, we don't really use orange or black moments, orange wrenches or black moments. We really only synthesize flexures and compliant elements that have pure force wrenches in them, the blue lines. That's what, of course, the one blue line is a wire, a plane of blue lines is a blade. And all the ways we generated parallel elements, they were all just filled with blue lines, okay? So if we get rid of all the orange lines and all the black moments, all the wrenches and all the black moments, and we also get rid of the constraint spaces that don't have enough independent blue lines in it to pass as a constraint space, then we get this. Okay, but first let me go back. The last comment I made probably is confusing. So check it out. Everything in column 4, 4 DOF, should consist of 4 degrees of freedom, and of course 6 minus 4 are 2 independent constraints. Well, here's a constraint space that does have 2 independent wrenches in it. Remember, it's a pure moment, and it's a blue pure force thing, and then all the wrenches in between with all the Q values, right? But it only contains a single blue line. Okay, so even though it's got a blue line, and that could be useful to design a wire, it only has 1 independent blue line in there, and it needs to at least have 2 to be a constraint space that can be used. This is another one. See, this is a cylindroid where its principal axis only has 1 blue line and the rest are orange. Okay, so since there's only 1 blue line in there, you know, even though blue lines are useful, we can't use this constraint space to design flexures because it needs to at least have 2 to satisfy 6 minus 4 equals 2. Okay, so what we're going to do is we're going to get rid of all the orange lines, all the black moments, and any constraint space that has, you know, less blue lines than 6 minus the number of degrees of freedom. Okay, if we do that, we get something like this. Okay, and then if we move things around because we now have space, all we did from there to there is just made things larger and moved them around. And then we're going to draw our black pyramid around it. Okay, when we did that, this everything in the black pyramid should look the same as before. It's the same good old fact chart that we used for all the previous lectures to design parallel things. And you know, there's no orange things, there's no black things, and all these spaces have plenty of blue independent lines to satisfy 6 minus the number of degrees of freedom. Okay. All the ones outside this pyramid, which is called the parallel pyramid, by the way, because you use it to design parallel systems, and you saw we used that in all the previous lectures. All the things outside the parallel pyramid are still freedom spaces that exist, that systems can achieve, containing all their rotations and translations and screws, but they don't have constraint spaces that can be used. They don't have any constraint spaces, even constraint spaces that had blue before we got rid of them. They don't have constraint spaces that have enough independent blue lines to synthesize parallel systems using those. So these are all the freedom spaces that do exist but can't be achieved by parallel systems. Okay? Like you might recall from, let's see, which lecture was it? I think it was lecture 4 or 5 or something. Anyway, I think it's 4. Yeah, I think it's 4 when we started looking at simple constraints and Maxwell's equation and these things, and we were adding wires into blocks, and I was telling you which degree of freedom does it kill and all those things. I gave you that trick problem where I said, you know, can you add a wire that just kills, you know, this degree of freedom 1 but leaves these other ones? And it was a trick problem. The answer was you couldn't do it. You couldn't achieve that combo with a parallel system. Well, it turns out if you're curious, you want to look back at that example, I believe it's 3DOF type 21 is the freedom space that I was asking you to design. And you can see here this freedom space, 3DOF type 21, doesn't have a constraint space. So there's no parallel flexure system that could achieve that, and that's why you couldn't stick a single wire in to get that motion combination. You would change it around and get a different freedom space within this parallel pyramid. So, okay, so but this is the fact chart for this lecture. This is the fact chart used for serial and often hybrid systems. Okay, well, really serial. Hybrid, you'd want to use the mathematically complete one. Okay, but this is kind of the new fact chart that's complete so far as we're concerned for this lecture. Okay, all right, so. Before I move on to the next topic, I just want to do some side notes about hoops because we brought them up with blue hoops as I was going to make my point in this topic. And you might ask yourself, well, what happens? I know if I take a red line to infinity, it makes a translation. And but what happens if I take a green screw to infinity? And what's a green hoop make? Well, I used to wonder. I used to think, well, okay, this is. You know, a screw is both translating and rotating. So it's like there's like some translational component along it, and there's a rotational component. So maybe it makes another screw in the center or something is what I used to think. But that's not true. What happens is, of course, all these translations, since they all point in different directions, they basically cancel each other out, and you just get the rotation. And so basically a green hoop is a translation. So whether you take a red line to infinity or a green line to infinity, they both make a translation. Okay? And by the way, that like the reason is not because the reason I gave you. That's kind of an intuitive reason for why it's a translation. That you can mathematically prove it just by taking a twist with a pitch that's like, you know, some finite value, push it to infinity, and you'll find it turns into a translation. You can also deduce that this is the case by knowing what spaces pulled to infinity turn into other shapes, and you can see very clearly that I can show you proofs of this when I get to lecture 11, that green lines pulled to infinity make translations very clearly. So I just gave you a way you can kind of think about it, why that's the case. So they kind of lose their translationness, and they just have the rotation, and it manifests as a translation there. Meaning they lose this translationness. Okay, and it just the red ones exist, and there's that. So okay, and by the way, also if you take obviously a wrench with the non-zero, non-infinite Q to infinity, it also makes a pure moment, just like a blue and orange hoops make pure moments. Red and green hoops make translations. Now, you might say, well, what if I pull a translation to infinity? Well, again, translations don't have locations, so there's nothing to displace or pull. They're just directions. And that obviously makes sense from hoop language, because if you ever try and move, you can only change the direction of the translation by orienting the hoop's plane in a different place. You can't move the hoop. It's already, all of its parts are at infinity. If you like move it over, this, you might say, well, this is more at infinity, and is this now in finite space? Like, no, it's always infinitely large. So you can't move a hoop. It doesn't make sense to move a translation. You can't move a translation to infinity. It doesn't have a location, right? It just has a direction. But blue, orange, red, and green lines, they do all have locations, and they can all be moved. And when they move to infinity, they turn into things with infinite pitch or infinite Qs, okay? So that's that. Okay, so but that wasn't the point of that section. The point of that section was to show you the mathematically complete fact chart, and to start showing you, the fact chart we're going to use for serial systems. Okay, so remember there are three kinds of systems. The definition of them is absolutely essential to getting fact to give you the correct answer, and therefore I've had to shape my own kind of definitions around what fact will make what will make fact true. Okay, so parallel systems are these systems here. They consist of two rigid bodies directly connected. Serial systems consist of parallel system modules, essentially stacked or nested in series. And you can see this is two parallel systems stacked together, and you get a 3 or 4, as many as you want, and it's still a serial system. Okay, and hybrid system is any other combination. Okay, so we're going to talk about serial systems in this lecture. Okay, all right. So here's a parallel guide mechanism, and it's parallel. And here is a serial version. Okay, and I'm going to talk about the pluses and minuses of parallel versus serial systems. So usually, if you can design a parallel system to do a motion, you should at least try it first, because it's usually going to be better. That's not always true, of course. Nothing's always true, like with these hand-wavy rules. But the reason is, first of all, it's easier to design, so it's going to be simpler. So you'll adhere to the principle of KISS, keep it simple, stupid, right? And it's going to be easier to fabricate. There's less stuff, less material, less weight. That's usually good. And there's also less complex dynamics. You just have one stage that's bobbing around. You don't have intermediate bodies that are bobbing around that you have to keep track of. Remember, parallel systems can't even be under constrained because they can't have redundant degrees of freedom. They just have the degrees of freedom of their stage, and that's that. You need at least two moving bodies to have, with the same degree of freedom, to have the redundant degree of freedom. And so there's just much less complexity. And if you can achieve the motion you want, you should probably make it parallel. Okay. However, there are some real advantages to serial systems, and it may be worth making a system serial. So first of all, you can get more range for the same size. So you can see these mechanisms have the same footprint and the same size, but the stage is nested inside of this one, and so, you know, whereas this one might move 1 centimeter, this one can move as much as that, as well as its own deformation. So it can move twice as far in the same footprint. Okay? And that's because it's under constraint. Remember, we talked about under constraint. The other neat thing about serial systems is not only can they move twice as far for the same range, or you know, a lot more, they can be carefully configured to cancel parasitic error. So remember, this guy arcs, and then this guy would arc if you hold that one fixed. So together, if they move together, they can essentially cancel, and you can get you know, rid of your parasitic error. That's another advantage of serial systems. But the real advantage of serial systems is they can access motions that parallel systems can't, as I've already kind of hinted to. Okay. So sometimes you're forced to. Sometimes, like, there's no parallel system that can get the freedom space, and so you need to make it serial or hybrid. Okay. Let me give you an example of one. So what if I, you know, systems where you get 3 pure translations with no rotations, no screws, nothing. Those are very valuable. Okay. Like, just imagine for like a 3D printer, it'd be nice if you had a stage that just moved X, Y, and Z with no rotations or anything. And you want it to be very precise, so you want it to be precision, flexures, and all these things. Well, it's very difficult to design a flexure that just has 3 translations and no rotations or screws. And you can see why, is because the second you add the simplest constraint, just a wire, say from ground to the stage, you just add 1 wire, well, guess what? You've already killed one of your 3 translations you wanted along the axis of the wire. So that should tell you that, you know, if you use the simplest constraint and you just stick it in something and it kills one of your 3, you're not going to be able to make it with a parallel system. Okay? And so to achieve 3 pure translations with no rotation, you need to do a serial, or in this case, this shows a hybrid. If you just did 1 arm here, then it would be serial. But because we add all these things in parallel, different combinations, and we do that to make it symmetric, to get rid of parasitic errors, by the way, you can get your 3 independent translations with no rotations. Okay? And I'm not saying this is necessarily a great design, but it will do what you want. Okay? 3 pure translations. All right, and it's symmetric, it's thermally stable, etc. So it's not a bad design. Okay. Okay, but the point is, we would expect to get 3 translations with no rotations or screws that are pointing in independent directions. We would expect that freedom space to not lie within the parallel pyramid. And you can you see where it is? First of all, you'd look in the 3DOF column, because it's 3 translations, and you'd go up here, and hopefully you'd come across this one, type 20, 3DOF type 20. That is a sphere of translations, and that's all that's in its freedom space. That's a very valuable freedom space, right? And you notice it doesn't have a constraint space. There's no way to, you know, just synthesize a parallel system from a constraint space that gets this, and so you can't have a parallel system. So it lies outside the parallel pyramid. You know, it's called the parallel pyramid, obviously, because these are the freedom spaces in here that can be synthesized, that have constraint spaces that can be synthesized with enough wires, blades, you know, flexure elements to directly connect 2 bodies together to achieve that freedom space. Then that's a parallel system, right? Okay, so let me teach you some other principles here before I tell you a systematic way to design serial systems, okay? First of all, whether you realize it or not, constraints in parallel, when they're arranged in parallel, they only maintain the degree of freedom that's common between them, okay? So I've hinted at this in the past, but I'm now explicitly telling you. Remember, this one is just a wire. It achieves a rotation and a translation perpendicular to it. Of course, this wire also achieves a rotation and translation perpendicular to it. Well, when you put them together in parallel, as you see on the far right, what you get is you know, the 2 translations have different directions, so they're not in common, so they die, they go away. What you get is what's in common with both of these, which is the rotation, and it would be at the instant center there. Okay? So degrees of freedom that they share in common, you know, I are the ones that survive. This is basically the rule I told you. Remember when I held up those models we made, and I said, imagine all the wires had disks of translations perpendicular to them, and find what translations from all those disks they have in common, and you'll find the translation of the mechanism. That was essentially this. I was saying find what they have in common. Visualize